very much. Thank you for the invitation. It's great to be here. It was very interesting. I think it's on. It's just maybe need to take it a little bit up. Yeah, I was hesitating until yesterday what I'll talk about, because I have to say I don't have something to do with thermalization, but maybe a little bit with entanglement. And so before I forget, I want to, so most of the talk will be about theory that mainly together with Sam Garrett, who is a stellar postdoc in Berkeley. And towards the end, I'll tell you a little bit about preliminary results we have on an experiment with Google about measuring post-measurement entanglement. So they approved showing it, although they like to keep things hidden for a while. So this is the group from Google, Noran, Isa, Elliot, and Pedram, and this is done also together with Yizhuang Yu and his student Wanda Wang. So, okay, so what I'm going to talk about is basically by way of introduction. Recent experiments have been kind of departing from the usual way we do experiments or measurements in physics. Usually in physics, measurements are used as a diagnostic of a state. So for example, in neutron scattering, we do a measurement at the end of the momentum of the neutron, and that probes for us some kind of intrinsic correlations of the system. So measurements are only a probe. On the other hand, in new kinds of experiments in quantum circuits, for example, or Rydberg arrays, you can have measurements that have, for example, mid-circuit measurements that influence the ultimate state. So during the preparation of the state, you create measurements that evolves the state by quantum collapse, basically. And that makes it highly unusual in various ways. First of all, we know that unitary quantum evolution is local. On the other hand, the quantum collapse process is highly non-local. So if you measure a quantum state, even local measurements of quantum states can create non-local correlations that haven't existed before or destroy non-local correlations. And the other thing that makes it unusual is that every time you do the experiment, you get a different state. So you kind of go on this tree where every node of the tree, every branching corresponds to a measurement outcome. So there are exponentially many leaves in this tree. You can, every time you do the experiment, you'd end up with a different state, and you can't hope to find yourself in the same state twice in an experiment. So how do we exactly diagnose the state, not as an average state, but really ask about correlations functions in a trajectory like that? So that poses a problem. Now, new experiments also force us to think more, more seriously about diagnosing quantum states, because first of all, the power of quantum states is the fact that they're highly entangled. Kind of quantum computing comes from the fact that we can have superpositions of a huge number of states. But of course, as we know, it's not so easy to use it, because first of all, extracting information about these coefficients, C1 to C to the n, is basically impossible. And every time I do a measurement, I kind of ruin this state, collapse it. And if we do another experiment, we're going to collapse it in a different way. So there is this makes it hard to diagnose states. So I think this led to a lot of work about how do we learn information about quantum states. And I want to separate into two categories. So one category where there is a lot of work is basically I have a reproducible state. Every time I prepare the same state, and I want to somehow do a tomography on it. I want to measure all possible expectation values but also nonlinear expectation values in the density matrix. Basically, I want to learn any kind of information I want, and there is a framework to do it using randomized measurements, so-called classical shadow tomography. This was initiated, for example, by this paper, but maybe more broadly. So using randomized measurements to learn about the state. On the other hand, there is also the other possibility that we're creating a state that is not reproducible because we're creating it by measurement. So this is an example. Suppose we start from a 2D quantum state that we generated from some circuit, and then we measure everything except for a few qubits. Here, an example of 2 qubits A and B, and we want to diagnose the qubits A and B and learn something about the 2-qubit state. For example, learn whether it's entangled or not. And it seems like an impossible task because that 2-qubit state is conditioned upon a very large, extensive number of measurements. We can't really, if we want to do a tomography on it, it seems like we need to wait an exponentially long time until we get sufficient large number of copies of the same state. Because of the no cloning theorem, we can't just clone it. So the idea is, okay, how do we nonetheless gain some information about this state when we're not able to wait for post-selection? So actually, I think the outline I gave here is from another talk. It's not accurate, but it's more or less what is it supposed to be. Sorry for the problem, but yeah. So first part of the talk, I'll actually talk about, first of all, what are measurement-induced phenomena. I'll give examples of measurement-induced phenomena, such as measurement-induced phase transition, and an even simpler measurement-induced phenomena, which are, if I take a ground state and I measure part of the degrees of freedom, but not all of them, and I can ask, how do the measurements affect the long distance universal correlations in this ground state? So these are two measurement-induced phenomena I'll show, and what makes them kind of interesting and unique is, again, the non-locality of the collapse of measurement-induced collapse. But both of them suffer from the same problem of needing post-selection to really probe exactly. So is there some way to circumnavigate it? And what I'll show in the next part is basically what is one, how to, is an approach that uses a hybrid method of quantum simulation cross-correlated with some classical processing in order to say something about the quantum state. And I'll show that I can give guarantees about the quantum state. So for example, without post-selection, I'll not be able to give the exact entanglement entropy between 2 qubits, but I will be able to prove, for example, give you a guarantee that these 2 qubits are entangled. I'll give you some bounds for the entanglement, actually both upper and lower bounds in some cases. So, and then I'll show how do I kind of efficiently get these bounds. We're going to use generative models, and we're going to show that I'm going to show an experiment where we're using generative models in order to learn about measurement induced states. So what I mean by generative models, well, okay, I'll just maybe slight preview is we have 2 qubit state. It's produced by a lot of measurements, conditioned on a lot of measurements. Suppose I have some classical agent, some agent or some being or you looking at these measurement outcomes. And after doing the measurement outcomes, making measurements on, say, random basis on these 2 remaining unmeasured qubits. And the question is whether if I do it sufficient number of times, but not exponentially large number of times with the number of total number of qubits, whether I'll eventually be able to make a prediction based on the outcomes of the preparation measurements about the wave function of the two remaining qubits. Okay, and the question is whether I'm going to be able to train a model to do these predictions. And what I'm going to show is that there are sharp transitions in the ability to predict these states. Okay, so first part, I want to talk about measurement-induced phenomena. And the first one, maybe quite famous by now, is measurement-induced phase transition. Many of you have seen these circuits as an example. It's the basic structure is a random circuit involving both unitaries, random unitaries, and measurements. The fact that the unitaries are random is probably not so important. It's not fundamental. The unitaries, even if they're random, they're the same every time I do the experiment. And the measurements, of course, give you random results according to Born's rule. The measurements are sprinkled around, so from time to time, by some probability p, per cycle, I measure a qubit. And then the question is, as a function of time, if I look at the entanglement entropy, if I don't do the measurements, of course, the entanglement entropy will grow linearly in time, the entanglement entropy between the two halves of the system. But when I do measurements, it disentangles part of the system, and it turns out that there is this competition in some non-trivial way leads to a measurement-induced transition between state which has unbounded growth of the entanglement linearly in time until it reaches a volume law, and the other in another phase where the entanglement entropy saturates to an area law, and you can do nice scaling in the numerics and show that it's really a bona fide phase transition. I won't go deeply into this, but one can start to understand these phase transitions. And here is where the fact that the unitaries are random and independent from site to site, by averaging over the unitaries, you can use Weingarten calculus to derive effective statistical mechanics models. So the question of contracting this tensor network generated by the circuit becomes the partition function of classical effective spins, except these spins are strange spins that instead of having just up and down, they generally have permutation values. So they're like permutation related spins, and the symmetry is not necessarily Ising, but it's Sn by Sn. And if you want to understand, in the end, information properties like von Neumann entanglement, you need to look at the hierarchy of these models and take the limit of the of n to 1, this replica limit. But you can understand qualitative features of the transition even by looking at them as Ising spins. In the case of that is what you get for Renyi 2 quantities. And in this case, the measurement of the purity corresponds to changing the boundary conditions between the two subsystems A and B at the top, from being down spins to up spins. And then you see that you can have two phases. If you're in the ferromagnetic phase, the domain walls, you force a domain wall through the system that has a free energy linear in the system size in one phase. And in the paramagnetic phase, it's order 1, and that gives you the change in the entanglement entropy. This domain wall free energy maps exactly to the entanglement entropy, which goes from linear in system size to order 1 in this one 1 plus 1 dimensional circuit. Okay, so this is the measurement-induced transition. There is another nice way to understand it as a learnability transition, which is if I think of this circuit as inputting some information from 1 qubit, and I want to, it propagates to Bob this information. However, there is someone that listens in and does measurements. And the question is, how much can she learn about the initial state from the measurements? And that information, that sensitivity to the initial state can be shown to undergo a transition where in the area law phase, when the probability of measurement is sufficiently big, it means that this Eve can learn the maximal amount of information about the state after listening in for sufficiently long time, while in the volume law state, in the volume law state, there will always be information that is hidden from her even after a very, very long time. So this is sort of a learnability transition. How much can I learn about the initial state from the measurements? What I'm going to talk about is going to be pretty similar to that. It's going to be how much I can predict the future based on the measurement outcomes. And that will also have a phase transition. And to understand the experiment we're going to do later, it's worth noting that there is another way to realize the measurement-induced transition and quantum circuit in a kind of non-dynamical way. And the non-dynamical way is to start from a two-dimensional state. The two-dimensional state is maybe produced dynamically, but it can be produced by a very shallow circuit. So you produce a two-dimensional state, and then you measure all the qubits at the top. And after measuring all the qubits at the top, there is no more dynamics. You measure all the qubits at the top except for 2, for example. And you can ask the question whether the 2 qubits that you haven't measured became entangled. So you start from a completely trivial state. You propagate for a finite time. Of course, you haven't generated entanglement long distance after a finite time. But after measuring everything, you induce entanglement at long distance. You could induce entanglement in long distance. That turns out to be exactly the same universality class, or exactly the same even one-to-one process as the measurement-induced transition. You can think of this two-dimensional state as encoded by some tensor network, and contracting the tensor network from left to right here, for example, generates dynamics that is exactly the same as unitary plus measurements. And the depth of this time evolution, if it's continuous time evolution, can be a tuning parameter for the phase transition. And the entanglement between the two states, or the mutual two remaining qubits, or the mutual information between them, maps under the statistical mechanics mapping to a spin-spin correlation, long-range spin-spin correlation. Again, if you're in the ferromagnetic state, which is the long-range entangled state, these correlations will be long-range, and you'll find that you've generated entanglement to arbitrarily long distances, while in the paramagnetic state, these will be exponentially decaying, and at long distances, there will be no entanglement generated between these two qubits. So this onset of entanglement is like the onset of the order parameter of ferromagnetic transition, more or less. But again, this is hard to experimentally measure for exactly this reason that I'm repeating all the time. It's because if you want to measure the entanglement between these two qubits, you need to somehow get a reproducible state, and you can't get it from here. So this is the post-selection problem. Okay, so in order to So now I'm going to make a small digression from entanglement quantities, and I'm going to think about simpler quantities to measure. First of all, because I think it's a cool result, and second, because I think it makes it more intuitive what we need to do in order to overcome the post-selection problem. So the digression is going to be a simpler problem even than that. Again, I'm going to start, instead of doing a dynamical circuit, I'm going to start from just the state. For my purpose, it was important in this paper that the state is quantum critical, but in general, it's not, could be any quantum state. I start from a quantum state. I do partial measurements. So I measure some of the degrees of freedom of this state, but not all of them. And then I want to evaluate the resulting correlations between the remaining degrees of freedom that were unmeasured. And I want to ask, how did the long distance correlations in this state change due to, how do the post-measurements change, post-measurement correlations differ from the original correlations? And in principle, they can change at long distances. Even the asymptotics can change, even if I only make local measurements because of the non-local collapse. And in the end, it's going to suffer from the same post-selection problem, of course, and I want to know how to mitigate it. So here is an example. An example is, let's take the transverse field Ising model in, say, 2 dimensions or d dimensions. It's described by some quantum state, maybe tensor network, but this is just a quantum state. It's a tensor. In this case, no measurements, it's just the state. If I want to ask what are the correlations, then, well, as probably all of you know, we have a really nice framework for this. The partition function is, or the generator of the correlations is described by action in 2 + 1 dimensions. In this case, the quantum Ising model is described in terms of a partition function of the classical Ising model in 1 higher dimensions. And these correlations are really correlations that I take in this classical Ising model at equal times, at tau = 0 slice, for example. Okay, so so now how does this picture differ when I make measurements on this state? So when I make partial measurements on this state, I can still write the same generator of correlations. It's the same d + 1 dimensional partition function of Ising spins, except the measurement results have basically pinned some of these spins at tau = 0 to their measurement outcomes. So I have a partition function of Ising model with some strange disorder that only occurs in a surface of codimension 1 at the time slice tau = 0. So really, I map the post-measurement correlations to surface criticality in a new kind of disordered surface, or defect, I would say. And the question is whether this can change the critical behavior, the critical correlations. Well, it depends if this surface defect is relevant or irrelevant. And a very simple example where it is relevant that I can solve exactly, just quickly, is the case of, say, 3 + 1, so 3-dimensional Ising model, where the one extra dimension is the imaginary time. So 3-dimensional Ising model, then criticality is described by a Gaussian model. And we know that before measurement, the correlations are simply decaying like 1/x², just by dimensional analysis. Measurement creates a relevant perturbation here, and then by using kind of known tricks in surface criticality, you can show that the non-local, there is a non-local change in the critical correlations, and now the measurement condition, the correlations conditioned on measurement outcomes decay as 1/x⁴ power instead of 1/x². So it's an example where you change the correlations at arbitrarily long distances. There are other examples. But again, it suffers from the post-selection problem, which I won't state again. And maybe the most important thing to note here is that I can't really average over, if I do the, maybe it is worth going over this. So what do I do here experimentally? What is exactly the post-selection problem? Here is my state. I do measurements. I get the post-measurement state psi m. Now I want to measure on that state some probe qubits. So for example, I measure an operator x on these probe qubits. It could be z, it doesn't matter. I measure the correlation function xi times xj. What I get is an outcome. Xi times xj specific for that measurement was either plus or minus 1. That's what I get. I can't probe xi xj expectation value because for that I'll need to produce psi m many times, and I can't. So you can ask, what if I just dumbly average over my runs of the experiment? If I do that, then immediately you can see that what I do is really trace of xi xj with the average density matrix, because the measurements are a quantum channel. So averaging over the experiments gives me the average density matrix, which is the output of this channel. Turns out to be just the infinite temperature state, but more importantly, it's just a finite depth quantum channel cannot change the correlations at infinite distance. So it also has like a Lieb-Robinson bound. There is no way I can change the correlations at long distance by a finite depth channel. So I really need to calculate something like this. I need nonlinear averages in the density matrix or in the state, right? So this is the, and this is really not possible without post-selection. So what can we do? Okay, so this is what, for example, this is what we want and can't get. So we're going to define an alternative quantity, which is a linear average, which I'll call the quantum classical correlation. So suppose I have some calculation, either a classical learning model, or it could be a simulation of some kind. It could be approximate, that every time I run the experiment, I give it the measurement outcomes that came out of the experiment, and it runs the model, the calculation, and gives me the classical estimate for the expectation value. That it can do, expectation value in that state. And now I average that answer over the runs of the experiment. Right, so what I get from this is this quantity, average over the runs of the experiment, is the same as averaging over measurement outcomes of something that is linear in the density matrix. So it's just a reweighing of this average, and right, by reweighing, so this is what's going on here, right? Every time I do the experiment, I get a different value of my xm. I match it together with my classical computation given m, and I produce this quantum classical correlator. Okay. Can you say again, what is the x? Yeah, this is the output of my computer program. That given the input m, given the measurement outcomes, produces an expectation value of x. It could be just an exact calculation. For example, if you know the state, the exact initial state, for example, it's a matrix product state, you can give it, what matrices to put there for these particular measurement outcomes, and you output expectation value xm. That's an example of an exact calculation, for example. And but maybe you can do a non-exact calculation, which I'll show later. And that gives you something. It gives you why it's good. We'll talk about why it's good. But first of all, if it was an exact calculation, it gives you exactly this. If you had an exact calculation, it gives you exactly what you wanted without the overhead of post-selection. So you can do that with just it's a linear average. It converges with central limit theorem in the usual way. Okay, so there is no problem of sample complexity here. So in some sense, it gives you a new paradigm for comparing experiment and theory in measurement prepared states, in post-measurement states. In traditional experiments, how do we compare data to theory? We have data points are expectation values. We can get expectation values from the experiment, and we can get expectation values from our theory. We call it C again, it's classical, and we compare one to the other. Here, we can't do that because we don't even have the baseline of being able to calculate an expectation value. So we have a different scheme. The different scheme is we can calculate something in theory completely. This I'll call the classical correlation. So I have the classical calculation. I can calculate a classical correlation, and I can, if I have the quantum machine, I can also calculate quantum classical correlation, and I can compare them, and that tells me how well my theory is doing, whether it's close to the experiment. But it's not, there is a problem here. It's not giving me any information about an intrinsic property, because both of these lines are model dependent. It's not giving me anything model independent. It is telling me whether my theory is good or bad in some, at least heuristic sense. So these are, so valid concerns are, first of all, if I'm able to do an exact classical calculation, then what's the point of doing this whole thing? Because I know how to calculate it exactly. If I don't know how to do it exactly, then what I get is model dependent. So what does this quantum classical correlation even mean? So these are valid concerns, and now I want to solve them. And the solution will be, so I want to learn about intrinsic properties. So here is my intrinsic property that I'll show I can learn about, and there are more. I can learn something concrete about. So suppose I have my state. So it's a quantum state. It's highly entangled. I can't really draw it classically, but then I measure some of it. Okay, and I have this subsystem A left and subsystem B left, and I want to know the entanglement entropy of subsystem A in this scheme. Okay, so I look at the reduced I make the reduced density matrix of subsystem A, and this is the entanglement entropy of A. What I'm going to define now are the following quantum classical versions or quantum classical estimators for that quantity, which I'm not able to extract without post-selection. I'm going to define quantum classical entropy of A and the quantum classical entropy of the whole system AB. Okay, these are cross correlations. Both of them are going to be easy to extract, and I'm going to prove a bound that the true entanglement entropy that I want is bounded from above and from below by quantities that I can get efficiently. Yeah, and the idea is to use a version of classical shadows here. So let's start from the quantity that I really want to calculate, but to measure, but I can't. It's the entanglement entropy. It's nonlinear in the density matrix. The idea is to replace the nonlinear part, log rho m, with a classical estimator of this, which is called log rho c. Rho c is the again the density matrix that I get from I get from some classical model, either computation or non-computational. And I'm going to replace this rho m with a classical shadow. And this is defined as a classical shadow. What I do is basically every time I do the experiment, I measure in a random basis. This is the random basis. This is the unitary that gave me the random basis. And yeah, if you remember, this is the classical shadow density matrix. It's a horrible approximation for the density matrix, but it turns out that the fluctuations have zero mean. So under linear averaging, it just goes to the density, to the true density matrix. And if I do average over measurement outcomes or over runs of the experiment of this new quantity with this replaced by the shadow and this replaced by the classical version, I get the quantum classical entropy. So this is the quantum classical entropy. This I can get in a sample efficient way. It's a linear average over measurement outcomes. This sigma are measurement outcomes for the density matrix, you can think of it. So now the bounds. The bounds are really easy to prove. I mean, first of all, the upper bound is essentially trivial to prove. If I write my quantum classical entropy minus the entropy m, you see immediately that it's basically the relative entropy, and the relative entropy is non-negative, and that gives me the upper bound. And the other bound I can get by using the monotonicity of the relative entropy. So the fact that the relative entropy can only grow if I include more degrees of freedom. So when I go from A to AB, it can only grow if I do it consistently. Namely, the rho C is rho C that I calculate for, I generate for AB, and from that I reduce to A. Okay, so if I do that consistently, then this gives me both an upper and lower bound. So, so I have both upper and lower bounds that are efficiently observable. It's okay to have noise and imperfect classical model, because I can basically the quantum classical entropy AB of the total system AB gives me the bandwidth of the uncertainty in the bound. Okay, so I can get the uncertainty of the bound from this, and also this quantity has its own bound on top of the entropy, the true entropy of AB. So this is actually a good quantity to variationally try to minimize, if I want to optimize a classical model to give me a good prediction. Yeah, so the idea of using this as a cost function for some model that tries to produce the density matrix. So I take a generative neural network model, for example. Every time I do the experiment, I'll give it the measurement outcomes, and it will also produce a shadow density matrix. Here I define it by rho S instead of sigma. This is a shadow density matrix I gave. This model will produce initially maybe stupid approximations for rho C, and together they will make up this quantum classical entropy. And I'll just gradually I'll just optimize it by changing parameters of my model to get a better approximation. So in principle, this gives me a way to, if I'm able to learn, and now I can look at phases of my system which are either learnable or non-learnable. In learnable phases, I'm going to be able to collapse these bounds towards each other. In non-learnable phases, they're going to diverge completely from each other. So for example, here, I'm not going to, I'm expecting that in the volume law phase, I'm not going to be able to learn the 2-qubit state, because if I'm not able to even compute this, it's an exponentially hard computation. I can't expect the, unless there is a way for to compute it that we don't know as humans, and somehow the neural network finds it, which it's hard to expect, then it's not going to be able to learn. In the actual experiment, actually, we're going to have, we're not going to start from a pure state, or in fact, we're maybe going to start from a pure state, but because the measurements are faulty, we're in the end going to get a mixed state. So it's worth also getting bounds for mixed state entanglement measures. One of them would be the coherent information from A to B, and one can show a bound that the coherent quantum classical coherent information, it's kind of a two-line to show, is smaller than the true coherent information from A to B. And another that Sagar has talked about is the negativity. It's another entanglement measure for a mixed state. And it's defined in this way. Here, I deliberately define it like that. It seems a little complicated, but it's not. Take the density matrix of AB, partial transpose on A, and then project to the subspace of this projector is a projector on the subspace of negative eigenvalues and trace, which is basically just saying it's a complicated way of saying the sum of negative eigenvalues and taking a negative minus here to have a positive state. Why am I writing it this way? Because now you see that it's kind of natural to write the quantum classical version by taking the nonlinear process of this projection to be dependent on rho c, and the other one to be the other density matrix to be the true density matrix for which we're going to replace by a shadow. The transpose is a linear quantity, a linear operation. So, and from this writing, it's also very clear that this is always smaller than the true negativity. It's a lower bound to the true negativity because you project onto the wrong subspace that includes also positive eigenvalues and not only negative eigenvalues. So this is also a bound. Okay, and how to produce a decoder? I mentioned there is two ways to produce a decoder. We can have simulation-based decoder, simulate the process for each run on a classical computer. In the worst case, it's going to be an exponential overhead from the computation time. Or maybe we can use a data-driven classical decoder, which will directly learn from the experimental data without even knowing what is the circuit that generates it. The first example I want to give is from like a computational decoder. It's going to be a non-trivial example because I'm going to show that it can witness the measurement-induced transition in 1+1 dimension, and the computation is not exact. So, but nonetheless, I can kind of asymptotically get the correct scaling properties in principle of the transition, and it becomes scalable. And the idea is to use as a decoder, basically as the classical estimate, use matrix product state calculation with a fixed bond dimension. So basically the way to do it is you have this circuit with measurements. Every time you, every step, you truncate back to a set bond dimension chi. This is called TBD. So you do this calculation with different bond dimensions. I draw both upper and lower bound. In this case, it's a different lower bound, but it doesn't matter. And what you see is that close to the phase transition, they basically diverge from each other. And it's actually not too surprising that you can decode the state in the area law phase, because in the area law phase, there is a finite correlation length. In principle, in order to do full tomography of the state, you only need the effect of measurements that occur very close to your the two probe qubits. So in principle, if you can do as many measurements that are like exponentially big in the correlation length squared, you get you get the full information. But there is it's less trivial to show that you can actually without exponential overhead in post-selection, get the critical properties properly. Because by this argument, you'd say the correlation length diverges at the critical point, and then I need all the measurements when it diverges. But in fact, you can we can show that actually it requires only polynomial resources even at the critical point. So here I'm taking the entanglement between these two qubits, the mutual information, if you want, between the unmeasured qubits at the critical point. It's supposed to go like L to some power minus alpha. It decays at the critical point. And you see that from this quantum classical correlations, by the way, this is not an experiment. So to produce the quantum data, we do an exact calculation. And this is why we cannot go to systems that are larger than, I think here it was 20 something, 24. Yeah, so these are the largest systems we looked at. Now I do the calculation with increasing bond dimension. So increasing accuracy, you see that with increasing accuracy, you can go to, you can see this power law down to larger and larger sizes. And then at some point it fails, but you go to higher bond dimension and you get, and you can do a scaling collapse and see that the scaling of the bond dimension with L is a power law. So you need the bond dimension chi star before it fails, goes like L to the power alpha, lambda, and lambda is close to 2. So this is kind of the polynomial overhead for calculating at the critical point. Okay, so in the last part of my talk, I want to discuss an actual experiment. And the experiment, in the experiment, we used generative model to do the decoding rather than calculation. So before doing the experiment on this measurement-induced transition, here is a warm-up experiment, which is, I think, kind of interesting on its own right. So for the warm-up experiment, we also want to generate measurement-induced entanglement. And morally, what we're doing is we're looking at this system that we generated bell pairs at even bonds or odd bonds, and then we measure in the bell basis in even bonds. And what that does, it creates bell pairs that you measure bell pair 1, bell pair 2, bell pair 3, and it produces a bell pair from the first qubit to the last qubit. But which bell pair it is depends, of course, on the measurement outcomes. So the question is, can we predict that state based on the measurement outcomes? So the circuit that implements it is very simple. It's basically a circuit that transforms from the computational basis to the bell basis, and then transforms back. So this is the circuit. After each run of the experiment, we simply measure here in the computational basis, and we measure in a random basis the two probe qubits at the two ends. Okay, this is a and of course you can see immediately that it's kind of easy to see that in this case, at least if all the gates were perfect, then what you would get is an effective unitary transformation from here to here. So this is a problem that's very easy to decode even without a serious calculation. So we know how to decode it in principle. But it's sufficiently non-trivial that it's not clear a priori that how well the generative model will be able to do it. And what we find is that we train two different generative models, one based on kind of an MPS, another based on attention mechanism, which is basically just GPT out of the box. And you see that both of them train. The MPS is very kind of natural here because we're basically looking at the state that is a low bond dimension MPS, and all it needs is to find the right parameters. And this is the attention mechanism is just we take a GPT out of the box again. And what I show here is as a function of the distance, what is the entropy? What is SAB that we manage to, what is the loss function we converge to is this. Here you see the conversion of this loss function, which is the quantum classical estimate of the 2-qubit entropy. So what we see is that it converges to the exact entropy obtained from full tomography. In this case, we can do a full tomography of the state. And we find that it basically obtains the right value as QC just exactly falls on the post-selection, post-selected. The reason why we can do post-selection is that there are just 4 possible Bell states we can get. So when we do enough measurements, we can always do post-selection. So we get the right result. And we get a moderate improvement of this result with using ancilla qubits for error mitigation. But then we can go only to about 15 range 15 instead of range 34. Okay, and now we can do the real thing and ask whether they're entangled, the two edges. So in terms of coherent information, we can see entanglement up to about 15 sites, depending on whether we use error correction or not. Kind of local error correction allows us to go up to 15 sites, without error correction, 10 sites. Beyond that, there is no coherent information between A and B, which means that you cannot use that state in order to teleport from A and B as a resource. But it doesn't mean that there wouldn't be some entanglement that is represented by the negativity. As long as the negativity is positive, there is entanglement, and up to 34 sites, which is the maximal range we had in this experiment, there is still a positive negativity, which guarantees the existence of the entanglement because of the lower bound we talked about before. So we can guarantee entanglement in these ensembles of states we generate with measurements up to 34 sites. If we had error mitigation, it could probably go beyond, and now we have better ways to do error mitigation, so we might be able to go beyond that. Okay, and the last thing is the actual experiment that we wanted to do is the measurement-induced transition on this, or teleportation transition on a 2D state, which can be where the complexity can be tuned continuously. And the way we continuously tune the complexity, here the strategy is we create a cluster state. So first do a Hadamard gate, then we apply these ZZ gates for some set time to create a cluster state. And then we want to measure the cluster state in a continuously varying, in principle, direction, so that if the direction we measure the cluster state is in the plane, XY plane, then the time evolution in the effective time evolution we get from contracting the tensor network sideways is unitary. This is basically measurement-based quantum computation. Measurement-based quantum computation is exactly based on doing the measurements in the XY plane. But if we go away from the XY plane, then the dynamics is exactly like doing weak measurements in addition to these unitaries. So you have unitaries plus weak measurements. And the strength of the measurement is changing continuously with the angle out of the plane. Actually, the angle here, theta, the way I define it is away from the z-axis. So pi over 2 is going to be the unitary case. Yeah, pi over 2 is unitary. Less than pi over 2 is unitary evolution plus weak measurements with measurements increasing in strength. And you can simulate that, but it's clear that it's going to give it. Here we simulated, this is a simulation, and it shows nice measurement-induced transition. This is the entanglement entropy of A. You see that it onsets as a phase transition. This is for very small system sizes, so no finite size scaling. But now let's see how it stacks up in experiments. So for this, we have very, very preliminary results. So far, only on a 4x4 cluster, hopefully larger systems later, and also a little bit more noisy than we want at this point. But so I can show you, but take it with a grain of salt. So this is the cost function we're minimizing, SAB. This is the kind of, I can say, ground truth. It's simulation of the 4x4 system with exactly the noise that we know we have in the experiment that was characterized. So we expect to get to this value. And these are two decoders. One decoder is just using a noiseless simulation. We get that. Actually, it's noiseless plus some epsilon noise, but this is using a noiseless simulation, and this is using the machine learning decoder. And interestingly, you see that there is a range of theta in the area law phase where the machine learning decoder is doing actually better than the exact simulation. How can that be? Well, first of all, the exact simulation gives us, we give it whatever gates Google told us they use. But actually, these gates are not exact. And the machine learning model, of course, doesn't care. It does whatever, it doesn't know what the gates are, so it can do better. And also, the exact decoder doesn't know about the noise in the experiment, and this decoder does. So it optimizes for those. So it's nice that the generative model can actually do better. And it looks like, and I think it's now no coincidence that they kind of cross in when you go from about the area law to volume law transition is around here. I think it's fortuitous that the crossing is at the same point exactly, but it should happen like that because actually the exact decoder is going to fail at least for the noiseless case, it's going to fail because it becomes exponentially hard to do. And this is basically the reason the machine learning decoder fails, because then it becomes really too complicated for it. And if you plot the negativity now to see that we have entanglement, you see that there is a peak in the entanglement. And when we scale up, we expect that this peak will become narrower and narrower close to the critical point, because in one side, you are in the area law phase, there is no negativity between distant sides. In the volume law phase, you find no negativity because for the decoder, the volume law phase looks like a mixed state, and it again has a completely mixed state, again has no negativity. And actually in simulations on larger systems, this is how this peak behaves. But this is what we have so far experimentally. Okay, so just to summarize, so we can learn post-measurement state using this quantum classical version of the entropy as a cost function for a generative model or for a calculational model, if we have one. And this quantum classical entropy is the uncertainty in the bound of the entropy. We can actually get the subsystem entanglement entropy of, say, some of the qubits, and the total entropy quantum classical estimator is the uncertainty in the bound that we have. But the main thing is that we can bound both from above and from below an intrinsic property like the entanglement entropy. And of course, the outlook is if we can do that. So I showed how we can do that in processes where it's easy to calculate, like the area law phase or the critical point. But beyond the critical point, these decoders fail. And there is, to me, an interesting question whether there are systems that are easy to learn but hard to sample. What do I mean? I will really need a quantum system to do the sampling for me and generate the samples with the correct probability. But if someone gives me a specific sample, I'll be able to generate the entanglement or the two qubit density matrix easily. If I can find a system like that, I think it will basically allow to show quantum advantage, certifiable quantum advantage. And maybe a related thing is, I think this will not kind of prove quantum advantage, but it's kind of getting close. I showed the measurement-induced transition in 1+1 dimension or two-dimension shallow circuit. There is also a measurement-induced transition in a two-dimensional deep circuit with measurements, mid-circuit measurements. In this case, we don't have any matrix product state calculation that can efficiently calculate the critical point. Maybe there is a possible classical calculation, but there is not one that we know about now. So if the machine learning model is able to kind of witness this transition, it would be pretty interesting, I think. So this would be maybe a next step here in this experiment. Okay, thank you.
So nice talk. So can you say, so here the experiment you've looked at so far is just like 2 qubits, one on either side of this cluster state preparation. If you imagine going to larger system sizes where now you have like a cluster of qubits which are unmeasured and another cluster of qubits which is unmeasured, does anything scale poorly in your protocol for this? I see. Okay.
Absolutely. Even if I had a reproducible state and I did shadow tomography for a reproducible state, that would scale the exponential, the sample complexity would scale exponentially with the number of spins in your sample. So that would be the same scaling in our case, maybe with a polynomial overhead, but it would still be, yeah, there is no math. So the reason why we wanted a 2-qubit property, but this 2-qubit property is still a many-body property in a sense. It's been produced by a many-body process, and it's related to some spin-spin correlation function in this effective stat mech model.
But you couldn't, for instance, measure sort of an extensive negativity. Like if you go to volume loss state, you wouldn't be able to measure an
I
extensive
wouldn't be able
negativity.
to measure that. But fortunately for the measurement-induced transition, we have witnesses that are not extensive negativities, right?
So I guess I have a question. So you have like these bounds on the entanglement from this like cost function. Can the same cost function bound other like gradient entropies or like expectation values of observables? So that would be like kind of like an observable independent measure of like how good an approximation is.
Yeah, there is a more complicated way to actually generate bounds on essentially any quantity. But yeah, there is a paper by Max McGinley, which is a follow-up to our paper, who basically showed under what conditions you can write down bounds to observables. And you can bound kind of a very broad classes of observables.
And it's all with this cost
Including
function.
Using, is it using this cost function? Yeah, this cost function is just